Welcome to the BTB Solutions 8-Hour Challenge. In each challenge, 2 of our engineers get just 8 hours to design, build, and make it work. The twist? They don't know what they're building until the clock starts. It's an unassuming morning at BTB Solutions headquarters. The team has convened for their daily morning meeting.
I'm coming off vacation at the coast. It was pretty good.
Business as usual, except it's not. Today, 2 unsuspecting team members will be handed a slip of paper explaining just what the challenge entails. And then, the clock starts.
BTB Solutions 8-Hour Challenge. The challenge: you have 8 hours total to design and build a robot that will kick a soccer ball as accurately and fast as a professional World Cup soccer player. Parameters: hit the target consistently with a soccer ball at a velocity of 70 miles per hour or faster.
There you have it. The challenge has been set. Build a robot that can kick a soccer ball with the speed and accuracy of a World Cup player. The target? Consistent hits at 70 miles per hour or faster. And they have to do it with just what's available in the shop. No special orders, no extra help, no outside resources. Can it be done? We're about to find out. Our lucky chosen 2, Kyle and Andrew. Kyle is in electrical and industrial controls. He designs the electrical systems and programs the controls for industrial automation robots at BTB Solutions. Andrew is a mechanical engineer. Andrew does 3D design work, layouts, drawings, and custom machine design. In his own words, if you can physically see the part or machine, he designs it or uses it to get the job done. With the clock ticking, Andrew and Kyle get to work hashing out ideas. First problem to solve: what type of robot will they build? Since BTB Solutions primarily builds robots for packing, sorting, and palletizing products efficiently, they will need to work within the parameters of the functionality of those robots. A key concern is velocity. How will they use a robot to generate enough force required to kick a soccer ball at 70 miles per hour? As they work through ideas, it quickly becomes apparent they will need to use a force multiplier in conjunction with the robotic arm to create the amount of force needed. Ideas are tossed around.
Like a motor would spin up the flywheel. Oh my goodness.
From a swinging arm attached to the end of the robot to a piston-style device that fires upon impact with the ball. But remember, there are limitations. Andrew and Kyle can only use what's available to them, and without a spare pneumatic piston lying around the shop, they went with another idea. So what idea did they settle on? That will be revealed shortly. With the clock continuing to tick, the men begin to look for supplies. Now, with less than 6 hours remaining, the build begins.
Just as fast as you can.
As fast as I can. All right, here we go. 1, 2, 3.
It seems so fast.
Andrew and Kyle landed on a pull start style device. Similar to the way you might pull a cord to spin the engine in the lawnmower, our robotic arm will pull a cord attached to a cylinder from one of our conveyor belts. That cylinder will be attached to an arm that will swing around and kick the ball. In theory. But ideas drawn up on a whiteboard don't always translate in practice. And with the build coming to an end, the clock ticking down to less than 2 hours remaining, it's time to begin testing the device.
All right, ready? Yep, go for it. 3, 2, 1.
Puzzles, no! You got this. Oh my goodness. Not dangerous at all. What do you mean? It's perfectly fine.
It's okay because Joel's our safety manager.
So.
With a successful manual test in the books, Andrew and Kyle move on to attaching the robotic arm and testing the device as designed.
Earlier we tried to wrap the strap around and just pull without duct tape, and it just slips off. Okay, you gonna catch it?
Everything seems to be going as planned, but how fast were they able to kick the ball? The men place a measuring stick on the ground and mark out a 6-foot distance. They film another test. Using slow motion video, they are able to see how long it took the ball to travel 6 feet.
Pull this up here, bring it right to the time. So let's play it safe. So we're at 8:17, crossed our measuring. So that was as I was entering. And now that I hit that mark right there, I'm at 9:04, 5, 6, so 6 feet. So we're at 6 feet in 0.87 seconds. What's this called where you do this? You got, yeah, exactly. So you got 60 seconds.
Kyle gets to work on some quick conversion math. The ball traveled 6 feet in 0.87 seconds. 6 feet divided by 0.87 means the ball was traveling 6.897 feet per second. Multiplying that number by 3,600, since there are 3,600 seconds in an hour, means the ball was traveling 24,829.2 feet per hour. There are 5,280 feet per mile, so he divides 24,829.2 by 5,280, which gives them a speed of
4.7 miles per hour. See, something's wrong there. Oh, but that can't be. That's impossible. Okay. So, revisit our calculation.
But this is also slow motion, right?
Oh, that's it. Okay, so
we're at 1/8 of the speed.
right. So what? How much?
So this is 1/8 of what it actually looks like.
good catch, guys. They also have to account for the slow motion video, which was filming at 1/8 speed.
So just
Multiplying 4.7 by 8 gives them an actual speed of
times 8. So 37.
37.6 miles per hour.
Yeah. It's crazy because it feels faster. And we're like only halfway there. I have to think about how we can make up that.
With time running out, Andrew and Kyle brainstorm ideas on how they can double the speed of the ball.
30 miles per hour, 33 miles per hour. So one thing I know we could do is so that's, like you said, manually jogging the robot. We can, with programming it, I can make it go faster. That should help. What else?
Adding more weight on them, like a golf club.
Okay.
Your driver's heavier, so it's gonna hit.
Absolutely. Okay. Yep. My thought is, as I might have to go kind of slow with the robot with all that cantilever weight at first to overcome and not just like destroy our super sturdy structure. So my thought is, if we counterbalance this and make it way easier for the robot to spin it, maybe we can get a lot more speed.
Increasing the speed of the robot as it pulls the strap and adding weight to the swinging arm to create more force impacting the ball is the strategy they land on. But the clock doesn't stop. And now, as the clock ticks into its final remaining hour, will they have time to make the modifications necessary to successfully complete the challenge? The modifications have been made, and it's time to test again.
Okay. And ready?
Yep.
All right, and go. Yeah! That's the best. All right, we won. Can we go home now?
Yep.
Darn it. Okay, fine. What now, Andrew?
Unsure of what went wrong, they quickly set up for another test.
I'm gonna do a down motion until it's tight. Here goes. Ready?
Yep.
Go. Yeah, it's definitely slipping, isn't it? Here's how I know. Because this is all loops now.
Oh.
And it did the motion.
So
So it was just either way too fast or we got to figure out a
too
better way to
spongy.
make this hold. Wait a minute. What did happen? Are you confused? That's what's happening. I'm so glad we looked at the video.
so
We were gonna be on the wrong dang track.
uh,
The
so this
bars.
bar is sliding inside.
So what now?
Weld.
That's exactly what they would have to do. With no other dependable solution to secure the U-bolt to the bar, Kyle gets to work welding it in place. But that takes time, and time is the one thing not on Andrew and Kyle's side.
Ready? And go. Oh man. So what happened? It faulted out. That's why. I think it didn't work because it faulted out.
Because of what they're asking the robot to do, the internal safety system triggered, slowing the movement of the arm and resulting in less than ideal results. Andrew and Kyle have less than 20 minutes to dial in the robot to get it to perform the way they need it to and avoid the collision detection system. Remember, their initial test kicked the ball at 37 miles per hour. They need to find a way to nearly double the velocity of the ball if they even have a chance at being successful. A series of tests ensue.
Here goes. Very underwhelming. Collision was detected. We're gonna get it perfectly lined up because this is gonna be perfect. All right, here goes. Faulted out again. Although that seems like way harder to overcome. Or am I wrong? Let's give it a try. I just messed up. Darn. Morale is low. Okay, ready? This is gnarly. This is probably our last shot maybe, and we just...
Nearly out of time, they set up for one final test.
Seems way slower. Well, that makes me pretty upset, but that's it, I guess.
Andrew and Kyle gave it their all, but time was not on their side. As engineers, this was a tough pill to swallow. They're used to finding solutions, no matter what the obstacle.
But that's okay because, well, that's okay with me because sometimes failures are more valuable than wins. I think we're onto something very good.
I think a quarter to a third of our time was finding parts. So the actual build and fine tuning, if we had another 3 hours, I think we could get there. We're close.
I really do think we're close. Any machine I've seen that that kicks a soccer ball robotically is a rotating one like this. 8 hours is a surprisingly short amount of time. Actual SI projects, custom robotics and automation, they're really hard and they take a lot of time and effort, and you run into challenges like this and you get stuck and you got to work through it. And one of my favorite quotes from a past coworker who I love, he would say, fail fast, and we didn't fail fast enough.
Well said, Kyle. With this BTB 8-hour challenge in the books, the men let off a little steam and get ready for the next one.
Get out of here.
Join us for the next BTB 8-hour challenge, where every build is different, no one knows who will be selected, and the clock is always ticking.